Howdy. We're going to continue talking about electronic energy bands in this video, and we're going to talk about now how do we fill up these energy bands with the available valence electrons, so the outermost energy electrons in the atom. And how does this filling of electronic bands result in the electronic properties that we're familiar with, so metallic, insulating, and semiconducting properties. We're going to pick up in where we left off in the previous video. So if you remember, we can start off with an individual atom that has discrete energy levels, right? So 1s has specific energy, 2s, 2p, 3s, 3p. These all have specific energy levels that the electrons would occupy. When we combine a whole bunch of atoms into a solid, the outermost valence orbitals of these atoms are going to start to interact and result in bands. So again, the core electrons, the 1s, 2s, 2p, are going to remain relatively unperturbed, but the 3s and 3p, in this model system that we're thinking about, the 3s and 3p individual energy levels are going to mix, and they can lead to a range of energy levels that atoms could take. And so these will be the bands that we'll think about. Now, I'm only thinking about the orbitals in this case, but the orbitals are going to be full of electrons to some extent. So first, let's think about a model where I have up to and including a partial filling of that 3s energy level. So the resultant core levels are all full. But I only have enough electrons to fill up part of one of these bands. So remember, the electrons in the ground state, they're going to fill up this lowest energy level first, and then they're going to keep on filling energy levels until I run out of electrons. So if I start off with the case where I only have one 3s electron and I combine a whole bunch of these atoms together, I'm going to have enough electrons to partially fill up this bottom band. And so that's going to look something like this. Now, what does that mean electronically? Now, for electrons to conduct around, they have to be excited outside of their ground state. So these electrons have to find some higher energy level that they can be excited to, and then they're free to conduct. If I'm partially full this, if I've only partially filled this band, remember it's a continuum of very finely spaced energy levels. So there are a lot of available unoccupied energy levels up here that electrons can get excited to. Remember, there's always thermal energy in the system, and that's enough to bump up these electrons a little bit to these unoccupied energy levels. And what that means is that this material can conduct very well. So this is the classical picture of a metal. We have a partially filled band. Electrons can very easily be excited up to unoccupied orbitals, and once they're in these unoccupied orbitals, I have an electron here, they're free to conduct around in a material. Now there's another way that we can get metals, and these are sometimes called semimetals, and that's when, given the energy levels of the orbitals, if they are such that those energy levels overlap, I can have two bands that will actually overlap. And again, I could start filling up these with electrons, but the important thing to remember is that in this case, again, there's a continuous spectrum of available energy levels, all the way from the very bottom, and these ones look like they're occupied up to about this level, and into this unoccupied energy band. So the important thing about metals and semi-metals is that there are unoccupied energy levels that the electrons can reach very easily because they're very closely spaced in terms of energy. And this results in a lot of free carriers, so a lot of free electrons that can move around and can conduct electricity. Okay, what happens if we have only enough electrons that when we start filling them up, we end up with a full valence band, but we don't have enough to start occupying what we call the conduction band. And this is the picture for a semiconductor. if this band gap is relatively small, and I start filling up, and I run out of electrons exactly where when I fill up this lower band. And so again, this is called the valence band. This up here is the conduction band. Now remember, I said in order for the electrons to conduct electrically, in order for them to move around in the material, they have to be excited up to higher energy level, unoccupied energy levels, right? But there are no available energy levels within the band gap. That's the definition of the band gap. There are no energy levels that the electron can take. So in order to conduct, this electron has to have enough energy to get all the way excited up here. And in semiconductors, this is difficult but not impossible to do. So I have a very small number of available carriers. And that's why semiconductors can conduct electricity relatively well under certain circumstances. What happens if I take this picture but I start increasing the magnitude of the band gap? So that was the semiconductor picture. If I start increasing the magnitude of that band gap, it's more and more difficult for these electrons to be excited up to the conduction band. This is what an insulator is. So an insulator is a material where we've filled up this valence band. We have available energy levels in the conduction band, but there's a very large band gap. And so it's very difficult to excite these electrons all the way up across the band gap to a high enough energy level that they're able to conduct around. Now, let's think about what different kind of materials could behave in those different systems. If I think about the alkali metals, they have a partially filled s electron. So these are all, they all have one available s electron. And what that means is that this bottom band is almost always going to end up partially full. So these are metals. Same thing in the transition metals. In this case, I have partially full d electron orbitals. And again, if I fill them up one electron at a time, I'm going to end up with a partially full band, and that means that there are energy levels that these electrons can get excited to. So these are largely behaving as metals. The alkaline earths are a little bit different because I would have a full s orbital likely. So for example, in this case, magnesium, I would have a full 3s orbital. But we think of these things as metals. In fact, we call them the alkaline earth metals. And so they do behave metallically, but it's a little different picture than the alkali metals or the transition metals. In this case, I have this 3s orbital, and the p or the d orbitals end up overlapping. And so even though I have a full s orbital, there are still available energy levels at slightly higher energy for these electrons to be excited to. So this was kind of like that semi-metal picture that I presented. Now, if I think about the traditional semiconductors, things like silicon, germanium, diamond is even considered a wide bandgap semiconductor. I have a picture that is roughly half full of electrons. So remember, let's think about silicon, for example. I have 4 valence electrons, and by the octet rule, I would like to have 8 for a full closed shell. So that's halfway full. And so what that means is that when I look at my band structure, I have exactly enough electrons to fill up that valence band, but I don't have enough to start filling up the conduction band. So the traditional semiconductors are things that are in column 4, or things that add up to column 4. So for example, gallium arsenide is a semiconductor, or aluminum arsenide, or aluminum phosphide. And they always add up to these half-full pictures. So we could call those the group 4 semiconductors. the combinations from here and here, I call those 3 5s. But all of these are leading up to the picture where I have this full valence band, I have some band gap, and I have an empty conduction band. And so then the difference between all of these semiconductors is largely, what is the magnitude of this band gap, and what is the nature of these electrons at the very top of the valence band, or the free energy levels at the very bottom of the conduction band. Okay, so in summary, I want you to think about the different kinds of electronic materials and how we get them from filling up these orbitals differently. So metals, we have a partially full band. It's very easy to excite electrons up to higher energy levels and to get them to move around. Semimetals, again, we have a band that is full, and we have unoccupied states immediately above that full band. So again, it's easy to excite electrons and to get them to travel around. Semiconductors, we have this band gap. Electrons need to be excited over the band gap, and then they can travel around. They can conduct. Insulators, that band gap is large enough that I essentially have very, very few free conductors. And so the result is that I don't have very much electrical conduction.